All right, so last several lectures, we have gotten a very good idea of how neural networks work, how we train them. And as you guys saw, so far we've been looking at a column of neurons. And one of the reasons we did that is so that as we set up the mathematics of its learning, it can be based on vectors and matrices. And so in very few lines of code, we can program the entire network, no matter how many neurons do we have, right? So this is this, my thing is tilted a little bit. So anyway, so this is our linear layer. And the idea was we can connect as many linear layers as we feel like it. Here's one more linear layer, one more linear layer, right? Until we get to the very last layer. And the number of neurons that we decide over here will be based on how many categories we are trying to classify our data. Okay, so last layer, the number of neurons is fixed by the definition of the problem. So if we are trying to solve a 10 class problem, there will be 10 neurons. If you're trying to solve a 100 class problem, there will be 100 neurons, right? So all of these, if I together feed them, we also have to create a loss function so that we know whether the output produced is proper or not, so that if it is not proper during training, we can go back and compare it to the expected output or the target output. So this is our actual. And we can go back and adjust all the weights. And this is how we set up and train the network, right? Once the network has learned, we can remove the loss and feed it some new data in whatever output it produces. If it is a classification problem, then usually we'll take a look at the maximum index of the neuron to decide which class is it predicting, right? So from a learning point of view, as we discussed, in the beginning, we started with a single neuron, 2 neurons, 5 neurons, and so on. And we individually computed the derivatives and went back and adjusted the weights and the biases. And our typical learning algorithm was, if you remember, was based on the gradient descent. So theta, if it represents weights and biases, so it will be theta minus lambda, which is our learning rate, times partial L, which is the derivative of the loss function with respect to one of the weights and biases, and together cumulatively we can represent each one of those in our math terminology as theta. So theta are our learnable parameters, right? Okay, so let's take another look at it. So if I, let's say, create a 2-layer network, right? So I'll feed in an X, and suppose I have one layer over here and another layer over here. Okay. So as we discussed, all the inputs, it doesn't matter how many, what's the dimensionality of the input, all the inputs will be fed to each and every neuron. And then from here, every neuron will feed to all the neurons in the next layer, right? So from a weight matrix point of view, if I express all the dimensionality over here, for example, let's say this is 50 by 1, and let's say we have 100 neurons over here. Let's say we have 20 neurons over here in the second layer. Then what will be the weight matrix over here? Remember our terminology was go to the output size first, then the input size. So this will be 100 by 50, right? Then there will be one more weight matrix involved over here. Let me call this W2 as an example. So what will be the size of this? Not 50, 20. We start from the output, 20 by 50. Because I have, oh, sorry, my mistake. And okay, this is correct. 20 by 100, you are correct. 20 by 100, because the 100 is the one which is connected before, right? Okay, so let's take a quick look, see if everybody remembers how you will train this network. So if we have a multi-class problem, okay, so let me see if I can move this. Okay, so if we have a multi-class problem, for example, in this case, there are 20 outputs, right? Then we have discussed a couple of loss functions so far. We have, for example, discussed a loss function called mean squared error. So if I call this output A2, and suppose the target is Y, then, so this is our target. Okay, for a mean squared error, we were typically using 0.5 Y minus, meaning the target minus the actual output square as the loss function, right? Okay, we also talked about our cross entropy loss. So generally, if you have a multi-class problem, then cross entropy loss works better. And if you recall, the formula over here was I equal to 1 to number of classes. So if C is the number of classes, in this example, what will be C? I have 20 neurons in the last layer. So C will be 20, right? So then we will go Y of I and A2 of I, okay? So whatever is the, for all these 20 lines, what is the corresponding expected output and what is the corresponding actual output? Sorry, I'm missing the log over here. So minus Y of I, log of the actual output is the cross entropy, right? Okay. So anyway, let's pretend it's a multi-class problem. Then we decided to use the cross entropy loss. If it is a multi-class problem, remember if I magnify each one of these neurons, right? There's a sum over here. There's an activation function over here, okay? And in the middle of the neuron, meaning after the sum, before the activation function, when we go back, the derivative up to this point, so from the loss up to this point, okay, partial L over partial, whatever this point is, right? What do we call this? Delta. Okay, so that is the definition of our delta. So now let me see if you guys remember, if this, so if it is a multi-class problem, what will be the activation function we will use in our last layer? Okay, pretty soon you guys will have an exam and I'll be asking you these type of questions. So my question is, for a multi-class problem, what will be the activation function in last layer? Softmax is the answer. That's correct. Okay, in one of the assignments, one of the lectures, we did the derivation of the delta. If this is the softmax as an example, then my question is, after we went through all the math of the deriving of the delta, so what is the delta? Anybody remembers? Very good. If we call this, for example, S of I, okay, so then this will be, each individual will be S of I minus A2 of I, right? sorry, y of I, not A2 of I. And if we take a look at all 20 of them together, we can write it as a matrix S minus Y. Okay, so that is the delta up to this point, right? Okay, so now let's go to the previous layer. Let's say we go to the neurons in the previous layer, okay? So if I again magnify it, put a summation and an activation function, okay? Now this activation function will not be softmax, okay? For example, this could be a sigmoid as an example. Okay, if we call the output coming out of over here as, let's say, A1, because I call this A2 coming out of the second layer, if I call this output as A1, so my question is, again, to give you an idea from exam point of view, what will be, so suppose this, I call it delta 2. This is delta 2. So what will be delta 1 then? Go ahead, give me the, what will it be? No, that's the formula for the sigmoid going forward, right? But I'm talking about delta is the derivative. Remember, by definition, okay, so to give you a hint, remember whenever we go backwards, right? If we have computed the, let's say, delta up to this point, to compute the delta over here, we always try to relate it to the delta in the following layer. So when I'm asking you what is the delta in this layer, which I'm calling delta 1, try to relate it to the delta in the next layer, which we called it delta 2. So what's the relationship between delta 1 and delta 2? Okay. So let me, if you forgot, let me give you a hint, further hint. Okay, let's forget the matrix form. Let's go to an individual neuron. Okay, suppose this W5 is connecting this neuron to this neuron. If I say this is delta 3, okay, and if I say this is delta 2 as an example, what's the relationship between delta 2 and delta 3? W5 times delta 3, provided the activation function is a linear function, okay? Now, so this is if it is a linear activation function. Okay, now let me ask you, what if it is a sigmoid? And if I call this output A2, exactly. So the relationship of delta 2 and delta 3 will be A2, 1 minus A2, right? Then further, delta 3 times W5. Okay. So so in short, if there's some weight connecting one layer to another, when we try to come up with this delta, so for example, this, okay, so definitely this W will be multiplied with this delta to get to this point, right? But that is provided this activation function over here was non-existent or was a linear function. Because remember, we go from here to here, like from a derivative point of view. Then if there's an activation function involved over here, we further have to go from here to here. So if there's no activation function, then it will be, in this example, delta 1 will be equal to delta 2 times W, right? But that is up to this point. Okay, but now I further have to go back in the activation function. So if the output is, let's say, A, then it will be further 1 minus A, whatever this output is, right? Okay. So now let's go back to my example, previous example. And so my question to you was, let me use different colors. Okay, so my question was the delta that we computed up to this, which we called it delta 2. We came up with this answer based on the softmax activation function, based on the cross entropy loss. Okay, because we had, if you go back in one of our lectures, we had derived that for a softmax activation function, cross entropy loss. If we go through all the math, it just comes out very simple. S minus Y is the delta in the softmax neuron. Okay, so let's pretend we know delta 2. So we have computed it like this. Okay, now we are going backwards to the previous layer. So my question is, if we call this delta 1, what is the relationship of delta 1 with respect to delta 2 if the activation function is sigmoid over here? So if this is sigmoid, okay, again, the way you can easily tell it is forget the sigmoid. If there was no sigmoid, what's the relationship of delta 1 with delta 2? Okay, what's the weight matrix that's connecting the two? W2. So it has to be W2 times W1, right? Now you have to be careful as you are setting up the problem. Remember, anytime we're multiplying matrices and vectors or matrices and matrices, the dimensions have to match. So let me see if you, in this example, my question to you is, what is the size of delta 2? So what is the size of delta 2? 20 by 1. There are 20 neurons, and it's the derivative in the middle of the neuron. So definitely 20 by 1. So coming back over here, I say this is 20 by 1. Okay, what do we, forget the multiplication by W2. What should be delta 1, the size of delta 1? There are 100 neurons over here, so it has to be 100 by 1. Where's my pen? Okay. 100 by 1, right? Okay, so now let's see, what do we put over here? If I say W2, what's W2? 20 by 100. So will this work? No, I cannot multiply 20 by 100 with 20 by 1. So what will I have to do to get to delta 1? You guys got it, transpose, very good. If I transpose this, then this becomes 100 by 20 and then 20 by 1. What will be the answer? 100 by 1, and the left side is already, we already know that left side should be 100 by 1, right? Okay, so, and similarly, it doesn't matter how many layers do we have. We can go back and back and back and compute everything, right? So, so once again, the matrix form, only thing you have to be careful is, as opposed to just going to a single neuron and then multiplying these things, the only thing that gets involved is sometimes you'll have to take the transposes as you go back. Otherwise, it's the same concept, right? Now let's go further. Let's put the activation over here as well, okay? So how will the activation function be involved over here, okay? What will be the size of A1? A1 is the output coming out of over here, right? We're calling it all of these A. So this is A1 of 0, A1 of 1. So what will be the size of A1? 100 by 1. Okay. So the question is, where do we put this A1? Because we want A1, 1 minus A1. Okay. A1 is 100 by ones. And so basically, this is an element by element operation. Because for every neuron, we are doing A1, 1 minus A1, A1, 1 minus A1, right? Okay, so the net result is, so what I'm trying to say, this is not a matrix multiplication. The net result is A1 will come out to be, A1, 1 minus A1 will come out to be 100 by 1, right? So if we go back over here, so my question is, where do I put A1, 1 minus A1? In the middle, in the left side. What was the final answer over here? 100 by 1, right? Okay, so again, this is an element by element multiplication. This is not a matrix multiplication. So I can simply put A1, 1 minus A1 over here. But don't do a matrix multiplication. The first element of this 100 multiplies with the first element of this 100. Second element, second element, okay? As you write the code, you have to decide which one is a matrix multiplication, which is an element by element multiplication, right? Okay, so anyway, with that background, hopefully it doesn't matter how complex of a network we set up. You will reason it, you will make sure the dimensions match, where we are doing element by element multiplication or addition or subtraction, and where we are doing matrix multiplication, right? Okay, so if I give you a summary of all the lectures that we have done so far. So our basic idea has been set up a network. It doesn't matter how many layers we have. Okay. Express the weight matrices and the biases and the inputs all in matrix or vector form, right? There will be some outputs over here, which will pass through a loss function. Okay, there will be some targets given to us, okay? And based on if it is a classification problem, most likely you'll pick the loss to be cross entropy because that has proven best in classification problems. The last layer, you will use softmax, okay? And then you will simply, if you wanted to train it, you will have some training pair data. X1, Y1, X2, Y2, right? So you'll have a lot of these training data. You'll feed each one of these data. You'll find out what is the actual output, compare it with the target, compute the loss. So there will be a forward function, forward pass over here, computing the loss. Then once you compute the loss, you will go backward. And once you have computed all the derivatives, then you will do theta equal to theta minus lambda partial L over partial theta, and you will repeat it many, many times, okay? Anyway, as we talked about it, you will use stochastic gradient descent algorithm, meaning whatever training data you have, okay, let's say you had 10,000 training data, okay, you will not feed this one at a time, okay, in a sequence. You will create it into batches. So for example, you'll pick a batch, let's say batch size of 4 or 8 or 16, depending upon the problem, right? So which means you will pick 4. So our typical approach was you will randomize it. Okay, so that all these 10,000 get mixed up, like shuffling a deck of cards. Then you will, once it is randomized, then you will go start picking 4, then 4, then 4, until you go to the end, right? Okay, once you have completed one batch of 4 in sequence. Now we are going in sequence, but because we already had randomized it, it's picking things in, not in the same order every time. So if we go through all the data, all these 10,000 training data, 4 at a time, feed it to our network, compute the loss, go back, and now the gradients that we are computing are based on not just 1 item, but 4 items, because we were feeding 4. So when we update the weights, we'll divide by the batch size 4, so that it's taking the average of those 4 gradients and updating the weights and biases, right? Okay, so if we go through one time through all the training data after randomizing it, this is called 1 epoch. Okay. Now we'll repeat this process. So generally we don't train it for 1 epoch. We'll train it for many epochs. How many epochs? That depends on the problem. It could be 20 epochs, 40 epochs, 100 epochs. If we train too much, it will overfit our training data, meaning it will start memorizing it, so that if we give it unknown data, it will not do as good of a job. So there is a particular number of epochs that we train. And typically, what we do is, if we take a look at epochs, we will take a look at the loss over here. And like I was saying, loss will start high and gradually will start to go down. Okay. The training loss, generally, the more you train, will keep going down. Okay. But what we do is our training data, we also pick, for example, if our training data is 10,000, we'll also create maybe 1,000 validation data, which we do not use during training. So every epoch, we'll we'll test it on the validation data, and then also compute the validation loss. And as I mentioned, the validation loss sometimes will behave like this, meaning if you keep training, validation loss also will keep going down. At some point, it will start to reverse. That is the region from here on, we are overfitting the model, meaning we should stop the training. Okay. Once we have determined, okay, this is where we should stop the training, now we will save that model at that point. And now we can give it X unknown and see how well it does. And usually that will be our best performing model, right? Okay, so as I mentioned, overfitting can occur due to many reasons, due to more training of the data. Okay, so one of the key things in deep learning is we want to create models which work best on unknown data. Okay, meaning we want to avoid the overfitting. Okay, so what were the techniques we talked about in this course so far? So techniques to prevent overfitting. Okay, one was weight regularization. Okay, where, as you saw in the loss function, so in the loss function, we will, for example, if we are using cross entropy loss, right? So we will say minus AI log of AI, right? And I equal to 1 to C, the number of classes, right? And then what will we do further? We will also add, for example, a weight regularization term, which essentially means if the weight is higher, the value of the weights are relatively higher, the loss will go higher. So we want smaller and smaller weights. So we often define one more parameter. For example, this could be gamma or whatever, or beta. So this is like a regularization parameter. Just like the learning rate, this will be fixed. And then W square, meaning all the weights that we have in our network. We don't do it for the biases, only for the weights. So automatically, to reduce the loss, okay, as you can see, model will pick weights. That have small values. Okay, and that helps us in preventing the overfitting. You can still overfit. It doesn't mean it's gone, okay? But it will create a relatively better model, okay? So anyway, that was one of the techniques to prevent overfitting. What was the other technique we talked about? Dropout. And this was proposed by Hinton, who won the Nobel Prize. Very simple technique. And what was the concept in dropout? So we'll zero out, suppose it was producing 0.2. So randomly we'll pick some neurons and we will turn their value to 0 only during training, okay? So dropout, keep in mind, only used in training. You will not take a good enough model and start zeroing it out. So only used in training, not in testing or validation, okay? From exam point of view, I may ask you if I gave you 3 layers in a network, okay? Which of the layers will we be applying dropout to? Not the last layer, but the first 2 layers, okay? So it is not applied to last layer because that changes the classification. So, and I gave you an intuition behind it. The intuitive idea was very simple. You have a soccer team with 11 players. You want to create a really good team. Remember, if they get a red card or one of the player goes out, so how can 10 players compete against 11 players? So this same idea. So let's make our 11 players to 9 players. Let them practice against 11 players. So you can see each one will learn to compensate for the others and become a better player. So that is the intuitive idea. So very simple idea, right? And the third thing, what is the third thing we have to do to prevent overfitting? Okay. See, I gave you an example. Let's say our data is linearly separable. Pretend it's a 2-class problem. X's and O's, right? Okay, and suppose there's a little bit of a noise. For example, this is a noisy data. This is a noisy data, right? If you create a model, let's say with 30 neurons, what it will try to do is it will try to accommodate each and every data item, and it will come up with a decision boundary, which looks like, you know, if let's pretend this is an O also. Okay, like this, right? So even though the training loss is really good, it has 100% of, you know, O's recognized correctly. But remember, some of these were noisy data. So picking a 30 neuron model, which is too complex, makes the decision boundary accommodate, you know, noisy data as well. It could be just a 1 neuron model, because if the data is linearly separable, 1 neuron model, even though the training loss is not as good. Let me see if I can draw it. So 1 neuron model may simply go like this, right? So even though it misclassifies these 2 data items, right? Perhaps this one is misclassified, that's okay. For the unknown data, it will do a much better job than a 30 neuron model, right? So what I'm trying to say is do not pick too complex of a model. Okay, and I'll give you one example of it. Okay, some of you are also in the natural language processing class and advanced deep learning class. So one of the, where we are taking a look at transformers as an example. And one of the data sets that we use to assess how good of an architecture that we have created, suppose you came up with a modification on the transformer model, right? There's a data set called sequential cipher, where we take a look at an individual pixel. So cipher 10 is like a 32 by 32 pixel data set. It's a color image, but we take a look at black and white set of pixels, right? So based on a sequence of individual pixels, so if we 32 times 32 is 1024 as an example. So if we take a look, put all the pixels in one, linearize it, right? So we can think of it as if we are feeding this as a prompt to a transformer model, like all these pixels, right? And now we try to see how good of a job is our transformer model doing in recognizing, is it a picture of a plane? Is it a picture of a boat? Is it a picture of a car? What is its classification accuracy, right? So I could create, for example, a 30-layer with, let's say, 12 heads inside this. These are some of the sizes of the transformers. So if I create a very large transformer model, I can demonstrate it to you that it does a very poor, it may do a great job on the training data, but on the test data, it will do a very poor job. On the other hand, if I simply create a 3-layer model with 3 heads, okay, which is very small, it will do a far better job than this 30-layer and 12-head model as an example. So do not make the model too complex. Bigger is not always better, okay? For the certain class of problems, right? Now, for, let me also mention this, for ChatGPT, where we are taking a look at, a huge amount of data. The bigger is better because the data is so large that even our biggest models as of today will not overfit, okay? But like I said, Cipher 10 is only 50,000 training data. It is not 50 trillion data like we have in ChatGPT. So, so in short, these are the 3 techniques: picking a model which is just right, not too small, not too large. Too large of a model will overfit, right? Okay, so those were the techniques, right? Then we talked about how can we make our model a little bit better, okay? And one of the techniques was, because we are training our models using SGD, and SGD, that too a batch where we don't make a decision to update the weights and biases based on one training pair, but we based on the average inside a batch, right? When we have a batch of data, right? So suppose here's one data, here's another data, here's, let's say the batch size is 4. Okay, so this is X1, X2, X3. These are training data, right? And another, okay. So if we make it go through layer 1, then layer 2, and layer N, and so on, right? Until we get to the output layer. Okay, so if this is our model, okay, one of the problems that we can run into is let's say some numbers over here in one of the training data items are, to give you an example, if we were doing image recognition, let's say most of the images were taken during proper lighting conditions, but some of the images are very dark, okay? So now that what will happen is, because of the mismatch in the training data, it will do a poor job in training our data, okay? So this is where we came up with a technique called batch normalization. Okay, so remember, if the batch size is 4, what does that mean? Okay, compute the statistic on each one of these numbers inside each training data, okay, in each dimension. For example, find the mean of these 4 numbers in the first row of our training data, okay? And then if, let's say the mean comes out to be 0.2, right? And suppose the value over here is 0.4. So then what we will do is we'll subtract each one of these by the mean in that row, and also divide by the standard deviation. If the standard deviation of these 4 numbers, let's say, is 0.13, we'll divide it by 0.13. So same way we'll go to the second number. If this happens to be 0.32, we'll subtract the mean divided by 0.13. So we keep adjusting these numbers so that relative to each other, okay, their differences are constrained, okay? Otherwise, like I gave you an example of images, right? Some of these will cause instability in our training. So batch normalization is you take a mean across the whole batch, and you take the standard deviation across the whole batch, then every data item is subtracted by the mean and divided by the standard deviation. Remember, each number, each row, so the first row will have a different mean, second row in our data will have a different mean. So is mean row-wise, not the column-wise. If column is each training data, okay. For those of you who are in the NLP course, the large language model course, okay, there we don't use batch normalization. There we use layer normalization. So let me clarify, why don't we use batch normalization over here? Okay, see, anytime you are taking a mean of the data, right, and dividing by the standard deviation, this technique works best, statistically speaking, if the sample size is large, is slightly large, okay? Meaning, if you had a batch size of 4, okay, then the problem is 4 is too small, okay? Because if one of the numbers, let me give you an example. Suppose you're taking the mean of 4 numbers. One number is 2, one number is 3, one number is 15, one number is 4, okay? So pretend this is our noisy part, right? If I took the mean, what will it come out to be? 2 plus 3, 5 plus 15, 20, 24, mean will come out to be 6, right? But this is, again, think of it, we took a picture in a camera and somehow there was like, somehow that pixel became very bright for whatever reason. There was a reflection coming from somewhere else, right? So you can see, it should have been, suppose this was 4. If this was 4, what will be the mean? 4, 4, 8, 3, 11, and 2, 13 divided by 4, it's 3 point something, right? Okay, so you can see now it is one data item has totally skewed our mean, and it will do now a terrible job. So anytime we do what we call normalization, see So normalization.
She's calling for that only. Meet center.
Anna, 111.50 that deposited in your cash app, Anna. I mentioned cash.
That I already sent to her the cash app photo.
So I
Okay, so anytime we do normalization basically means adjust the data so that the different data items are relatively close to each other, right? And in all of these normalization techniques, if there's a data item x of I, we'll subtract it by the mean and divide by the standard deviation, right? So in normal image processing, we do batch normalization, meaning across the batch, we will take the mean. Okay, so as I mentioned, suppose you had two choices. You had a choice of batch size of 4 and batch size of 16. My question to you is, and pretend you have enough data, which one will work better from batch normalization point of view? 16 will work better because even if one of the data items is relatively off, there are 15 of them to compensate for it, okay? So batch normalization will stabilize the data, will result in a better stable model, which will perform better on unknown data, provided you use a bigger batch size, okay? So anytime we do image processing type of applications, suppose somebody's analyzing, cancer images or self-driving car images and so on, and suppose you have a lot of training data, make sure your batch size is 16 or 32 or 64 or 128, so that your mean and the standard deviation are more representative of the mean and the standard deviation of the data, and one noisy data does not skew the whole thing, right? Okay, so now just for your information, so that if we are creating a transformer architecture for natural language processing, like I was saying, we don't use batch normalization, we use layer normalization. So what's the difference? Okay, in layer normalization, we do not take the mean across the batch. Like, see, this is our batch. Like, these are the different data, training data in the batch. So here what we do is we go to, in layer norm, we will take the mean across over here. So if there were, let's say, 50 numbers we were feeding in one training data to our model, we'll take the mean across this way and divide it by standard deviation. So every data item is adjusted individually without looking at the other data item, okay? So within that data item, if one of the numbers was noisy, the idea is, or one was too big compared to the others, the idea is to stabilize that, make it relatively close, okay? So the question is why? Why in natural language processing, why don't we use batch normalization? Why do we use layer normalization, okay? And the answer is, the reason is more practical. Okay, the reason is, for example, if you take a look at ChatGPT, the ChatGPT 3.5, as an example, had a model size of 175 billion parameters, okay? Okay, which means any data you feed through the model, it has to go through 175 billion, weights and biases, to get to the output, right? So there's a lot of computation being done. If we are training ChatGPT and we make it, okay, we'll use a batch size of 32, okay? In our current technology, unless we go to quantum computing and we say, oh, it doesn't matter, it will do everything simultaneously, right? So because of the computational requirements, we use a very small batch size in NLP. So in NLP, the batch size is very small due to practical reasons because the models are bigger, okay? If the batch size is small, then like I said, does batch normalization make sense? No, it will in fact make it worse, okay? So that's where, on the other hand, for example, if we take a look at each training data item, right? For those of you who are in the NLP class, we have a concept of an embedding dimension. To give you an example, ChatGPT 3.5 used an embedding dimension of 4096 as an example, meaning there are 4,096 numbers in each training data, okay? So it makes sense to do the average and the standard deviation across the embedding dimension. So anyway, that's why that's called layer norm, where we do it across the embedding dimension, but for images and so on, we use batch normalization to do a better stability in training, okay? So to summarize, batch normalization is what we went into detail, okay? So if you recall, we modified our neuron. Normally, we have a summation going in each neuron, right? Okay, so if you recall, we came up with 2 extra intermediate layers before we passing to the activation function, right? For example, this will do the subtraction by the mean divided by the standard deviation. Then this was further will do a little bit of a scaling and a shift of the data, right? So this will do scaling and shift. Okay, so the question was, how does so this addition of the batch normalization sublayer over here, how does this change our training? And because previously, remember, it was easy to compute the delta over here. Okay, so we said, okay, let's create one more. We called it delta BN, if you remember in one of our previous lectures. And we went through the whole math of, computing the derivatives over here so that we can relate this delta BN to the normal delta over here. In the end, we came up with some equations that you programmed in or are programming in assignment number 4 to see that, right? So again, keep in mind, batch normalization. So if I ask you on the exam, okay, what's the difference between batch normalization during training and during testing? So what would be your answer? Okay, so again, batch normalization, what does it mean? We are feeding in a batch of data. And across the batch, we are subtracting from mean of all of these and dividing by the standard deviation, okay? In training, do we use a batch size? Yes. So for example, it would be, let's say 16 as an example. So there is a batch size in training, right? Is there a batch size in? No. So no batch size over here. Okay, So does that mean we should remove all of this? No, because the model was created based on, certain adjustment of the data once the sum is produced. So if you remove that in testing, it will not work. Okay. So the answer is during training, as we keep training it, it keeps learning these gamma beta parameters that we had talked about, the scaling and the shift. And those are the ones, and from whatever the overall mean of all the data, training data, and the overall standard deviation, that's what we will use in testing. So there is a difference between what these parameters are between training and testing. And again, as you do your assignment number, I think it's 4 or 5, I forgot, where you were doing batch normalization. Was it 5? 5. So in assignment number 5, pay attention to what is the difference, how is the model treating it differently during training and during testing, okay? And again, the reason is because there is no batch size, but that doesn't mean we eliminate everything. We have to go by what was the overall mean of the data, because if we give it an unknown data, it still has to subtract the mean and the divide by the standard deviation. And that is the mean and the standard deviation that it was learning. So during training, we also keep updating our overall mean and overall standard deviation, as you will see, okay? Okay, so the point is with all these concepts that we talked about, okay, your fundamental knowledge of neural networks, in my opinion, is one of the best in the world if you, understood it. And I sincerely mean this because there's a lot of material on the internet. They do a good job on some part, not so good job. And, a lot of times people, when they learn something, they try to be mechanical. Okay, this is the procedure. I got it to work, right? So it's like, when you go through your calculus courses or probability courses, if I gave you x squared, the integral is x cubed over 3, right? Or the derivative is 2x. But what is an integral? What is a derivative? Once you start understanding those, then you start to see, where do I use it, right? Very similarly over here, why do I want to use batch normalization? What will happen if I reduce the batch size? Okay, at least now you have an intuitive knowledge of it. So now, to summarize, our fundamental knowledge is pretty solid now. Okay, now let's go to the next level. So now we will go to the intermediate deep learning. Okay, and see, how do we make now more powerful models, okay, rather than just creating a 2-layer model or a 3-layer model, okay? And let me also mention this. In the beginning of the course, I had mentioned that there was a universal approximation theorem. Okay, that was proposed in the sometime in the late 80s or early 90s, I forgot, which basically said that 2-layer neural network can learn any complex function. Doesn't matter how complex it is. Okay, and again, provided enough neurons are used in hidden layer, right? So in other words, what this universal approximation theorem told us is that all we need is a two-layer network. Okay, if somebody says, "Oh, I created this 5-layer network and it does a great job," it's not because it was 5 layers. It is because whatever the function it learned is best for that type of data that you are trying to recognize, right? But somebody, instead of these 4 or 5 layers, somebody could have said, "Oh, just put this one and it will work equally well." That's what the universal approximation theorem says, right? So coming to our deep learning, what do we mean by deep? Deep means many layers, okay? So if mathematically it has been proven that 2 layers are enough, what's the point of deep learning, right? So as I had hinted to you in the beginning of the course, in the early 90s, neural networks got very exciting. You know, everybody said, "Oh, this is AI." Okay. Then as soon as this theorem came up, was given, when people said, "Oh, all we need is two-layer network." So all the AI excitement went away until, 2005 and so on, when convolutional neural networks were introduced. And it was demonstrated that no, actually, if we use many, many layers, sometimes even thousands of layers, it does do much better job than just a 2-layer network, right? So how is that possible? Okay, math, you cannot argue with. If I say, if 2 + 2 is 4, it always will be 4. Nobody can say, "Oh no, now it is 5." Okay. Uh, um, but anyway, so how is it possible that now in deep learning these days, we use many, many layers? And the answer is, now we will introduce convolutional neural networks. And as you will see, the fundamental idea is we will have a CNN layer now. Okay, so let's say layer 1. Then we'll have a CNN layer 2. And we will put many layers. Okay, right? But the important thing to keep in mind is that these layers are transforming the data. They are not learning the decision boundary, okay? Because if they were learning the decision boundary, then, like I said, we cannot violate the universal approximation theorem. So each layer is basically transforming data so that later on, clearer or better decision boundary can be created. Okay, so each one of these layers is again adjusting the data in such a way so that once we go to at the very end, you will still see a 2-layer network. So this 2-layer network will do the classification. Like I said, according to universal approximation theorem, we only need a 2-layer network to do the classification. We don't need anything else, right? But rather than applying this to the input data, what we did is we kept passing it through these layers. So each layer is just moving or adjusting the data so that by the time it comes over here, it is very easy for this classification layer to see what is the decision boundary it has to create to recognize between different classes. Okay, so deep learning is basically, like I said, regardless we use a transformer architecture, regardless we use CNN, regardless we use a state space model, which is getting a lot of attraction in recent days, it doesn't matter. All the previous layers, whether they are transformer layers or CNN layers or state space layers, all the previous layers, they are doing a transformation of the data, okay? In all of these cases, if it is a classification problem, there will be a two-layer network involved at the very end, which will take a look at all these refinements that we did to the data so that it can easily separate them out into the classes, okay? So at a high level, that is the idea behind deep learning. So I'll give you a short break, and after the break, I'll start on CNNs. Again, we'll go through nicely understanding what is the idea, and then we'll contrast it with transformers as we go in towards the end of the course, so that in the next courses, you can really understand how do we apply these to large language models and so on, okay? All right, let's take a short break. Resume the recording, share. Okay, so next topic we were going to cover is, as we discussed, now that our foundation for the neural networks and training of these and learning of these is done, now we can move to the intermediate level of deep learning, which is what are convolutional neural networks. And before the break, I mentioned the fundamental idea is convolutional neural networks will have many layers involved. And what each layer will do is it will enhance the input data in a certain way, such that as we go through many of these enhancements, it is very easy for the final classifier to distinguish which category the data belongs to if it is a classification problem. So typically convolutional neural networks we use for classification problems, even though they can be used for other type of problems, but they are really, they perform very, very well on image type of data, okay? Not so on natural language processing type of data. And why that is, once we go into the in-depth understanding of the CNNs, then we'll talk about, okay, why doesn't it do such a good job on text type of data, and why is it so good on image type of data, right? Okay, so the whole idea of convolutional neural networks is based on the concept of convolution. So I'll quickly give you a high-level idea of what exactly is convolution, okay? So convolution is a mathematical concept that over the years, as we study nature, we find that in nature, for example, our human vision system, we suspect is using convolutions to understand images, as an example. So that's where the intuition came in play. And also, as we study many different systems and in nature, we find that there's a class of systems, for example, our hearing, our vision, and a lot of other things in nature. Some of these go into the category of what we call linear system, okay? In a linear system, we have some input, which is a function of time, okay? And then we produce an output, which is also a function of time, okay? So linear systems, further are divided into categories, but the type of systems that we deal with are causal linear systems. Causal basically means it cannot predict the future, or, it's whatever output it's producing is based on the past. It doesn't know anything about the future. So output is based on current and past data. Okay, so what we did is, as we studied these linear systems, we found that the way they behave is the output produced by the linear system is a convolution of the input. Convolution, we typically write it as a X with a circle in it, so that means convolution. So output is produced by the input, convolution with H of t. And what is H of t? H of t is called the impulse response of the system. Okay, so what exactly is an impulse response? If you're coming from electrical engineering background, this is easy, but for people coming from a computer science background, an impulse is a mathematical function. There was a very famous mathematician named Dirac, who came up with this delta function. This delta function is called the impulse function. They're the same thing. And it's a very simple function. Delta function it's drawn, so if this is time, it's drawn like this. Okay, like a arrow going up at t equal to 0. Right? And this is called delta of t. And this is why they call it the delta function or the impulse function. Okay, so the delta function is kind of interesting. The magnitude, meaning what is the height of this pulse that appears at t equal to 0. So the magnitude of it, or the height of it, is actually infinity. Okay. The width of it, meaning how wide is this thing that appears at t equal to 0? Width is 0, right? So remember in math, if you do an integral of a function, what does integral mean in practical terms? Area under the curve, right? So if something has, for example, let's say this is 2, this is 3. If I did this is some function f of t. If I did an integral of this, what will I get the answer to be? Easy. What's the area under this? What's this area? 2 times 3, 6, right? And you can easily verify it. It's basically 2 dt going from 2 to 3, sorry, 0 to 3. And if you do the math, you'll come up with 6. Okay, that's what integral is, area under the curve, right? So now, what is the area under the delta function? If I do integral of delta of t from, let's say, negative infinity to infinity, right? What will this be? What's the height of it? So magnitude is the height. Infinity. What is the width of it? What's 0 times infinity? It's undefined. Okay, in math, it's nobody knows, right? Okay, but Dirac said, no, the way this function is, if we integrate it, meaning area under the curve is 1. Okay, so now coming back to the way nature behaves is, if I give this input to be delta of t, okay, and I observe the output, okay, that output if I call h of t, okay, so that h of t, which is the output based on the input of a delta function, is called the impulse response of the system, okay. So h of t is the impulse response, meaning, what does that mean? Meaning output observed when input is delta of t. Okay, so let's pretend you were given a system, okay, and you feed in an impulse and you find the output, whatever that output is, okay? We call it h of t, okay? Now you are given a goal, okay? What if I give it some new input x of t? It doesn't matter what that is, whether it's a sine wave, cosine wave, exponential function, it doesn't matter what that x of t is, okay? Then the output, so this is our output, from the system will be what? According to the law of nature, it will be x of t, whatever that new input is, convolution with h of t, okay? So now let me put in detail in it. What exactly is the convolution, okay? So convolution is, okay, so in math, now let me put this, the equation for it. So this is equal to negative infinity to infinity, x of tau, h of t minus tau, d tau. Okay, so this is how the output will come out to be. So this is what we call the convolution integral. Okay, so you might say, oh, this looks intimidating. Let me make it very, very simple to understand what exactly this is. Okay, so I'll pick an example to show you what convolution does. Okay, so let's say I have one function, and suppose this is, let's say something like this, -1 to 1, okay? And suppose this is x of, or let me make it h of t. So let me make it h of t so that's easy to see, okay? And suppose what I want to know is if I give it an input x of t, okay, what will be the output from my system? So suppose this is 3, this is 5, for example, okay? And the magnitude is 1, okay? So as I mentioned, the output will be minus infinity to infinity integral of x tau h of t minus tau d tau, okay? And remember, what was the physical meaning of the integral? Just the area under the curve, nothing special, okay? Now let's take a look at x of, so first let's focus on h of t minus tau. So if I draw h of minus tau, all I'm doing is changing the t scale to a tau scale, okay? And flipping this, so this becomes this way as I do the minus, okay? Because see, if x is 1, it is, it will be the same as x of -1. If x is -1, it's the same. So basically, you know, think of it this way. If I had something like this, suppose this is g of t, what will be g of minus t? It will get flipped along the y-axis, okay? So because I picked a symmetric h of t. If I flip it along the y-axis, it will still stay the same. You guys agree? So h of minus tau will be same as this, -1, 1, and the t scale becomes tau, right? Okay, let me do the same thing to x of t. So this was x of t. Because I want x of tau before I multiply them and integrate them. So what will be x of tau? X of tau will still be t. This was t before. It will become tau. I'm just changing the variable. So it will still be the same 3, 5, and the magnitude is 1. So this is x of tau, right? Okay, so now what I'm going to do is I'm going to see what does h of t minus tau do, okay? If t is 1, what it does is it starts shifting this to the right. So t is basically our shift amount. So t is 1, our function will move 1 to the right. If t is 2, it will move 2 to the right, okay? So essentially, as you can see, as t increases, okay, for different values of t, this function is moving to the right, okay? So as you can see, the convolution is basically multiplying these two things. So at t equal to 1, my question is, if I multiply these two, what will be the answer? See, at t equal to 1, let me use a different color. T equal to 1, like I said, it has moved 1 to the right. If I multiply the black part with the blue part, is there anything intersecting? No, because before I do the integral, I'm multiplying the two values. So the answer is 0, okay? As you can see, this is at t equal to 1. As you can see, as I keep increasing t, this thing starts to move towards the right. Only when it reaches t equal to 2, right? Because remember, it's one more over here. Then there will be an exact, right? So from t equal to 2 up to t equal to, let me see, what will be the value of t once it has passed this? This will be t equal to 6, right? So if I now multiply these two, when will be the maximum overlap? Maximum overlap will be when at t equal to 4. You guys agree? Okay, so at that time, when I multiply, let me make one a different color. If I multiply this green with this blue, the answer will be just this part. And that's the area which is this integral is basically computing the area after the multiplication. So if I plot this out, what you will see is the answer of the convolution will be at t equal to 2. It will start to increase. Maximum overlap will occur at t equal to 4. Okay, then because now it is moving away, so then at t equal to 6, it will go back to 0. Okay, so to summarize, okay, you don't have to worry about the, like I said, convolution, all it's doing is sliding it, multiplying it with the other signal, okay, and then seeing how much is the overlap, and then it's integrating it, which is basically seeing how much is the amount of overlap. That's all convolution is. So where did it produce the highest value between the two? You can see as I start sliding it, once this thing reaches this part, right? That's when there's a maximum overlap. And if you measure the convolution right at this, it has the highest overlap at t equal to 4, right? So you can intuitively think of the convolution as, okay, like one aspect of it. Not it has another aspect as well. So one aspect is it determines at what point there is maximum similarity between two things. Because the value of the convolution is the highest at that point, because the overlap is the maximum and the integral is simply computing the overlap, right? Okay, so from our point of view, like I said, don't worry, even if you don't, the integral is too intimidating. Integration is just an area under the curve. In this case, area after we determine the overlap, because we are multiplying these two things. So after we multiply, then we integrate, right? So to give you a very easy example to understand, let's say I have one image of some soccer game being played, and here's the soccer ball. So this is some image. Okay. And my goal is to find out where exactly is the soccer ball in the image. I want to know the exact XY coordinate. Okay. So take a look over here. What if I create one more image of just the soccer ball? Because that's my goal. Okay. And I do the convolution between these two. So take a look, what will it do? I remember, what did I say? What does the convolution do? Let's go back over here. What's the first thing it does? Slides it. So think of it this way. If I'm doing the convolution of soccer ball with, there's many things over here. There's some players over here, some, so it doesn't matter what there might be a tree over here. All I care is where is the soccer ball. So if I created the soccer ball image, okay, and this is the given image. So this is soccer is my, and I want to do a convolution between these two things. So as you can see, what we'll do is we'll start sliding the soccer ball over here. So in the beginning, the soccer ball will be over here, right? And it will do a convolution with the background. Okay, and what exactly is convolution, as we discussed, is area under the curve. Okay, for continuous signals. Okay, so convolution is this integral is area under the curve after multiplying two signals. So this is in the continuous domain, okay? But when we go to the pixel domain, each pixel is individual, right? Each pixel has a value 0 to 255. For example, first pixel over here in the background may be 117, second pixel may be 85, right? So the convolution so this we call the discrete domain, because pixels can only take a value on a fixed range, like 0 through 255. So in the discrete domain, the convolution becomes multiplication and summation. So multiplication of two inputs. And the integral gets changed to adding them up. Okay. So to give you an example. Okay, let me pretend the background. So let's go back to this image. Okay, background is like this. The pixel value is 10, 5, 0, 20, 0, 10, 20, 30, 0, 0, let's say 10, 0, 1, 5, 10, 20. I'm just picking some pixel values in the top left-hand corner. So these are the background pixels in given image. In the top left-hand corner. And let me assume the soccer ball image that I created is also 4 by 4 pixels. So the soccer ball image, let's suppose the pixel values are 10, 20, 30, 40, 10, 10, 10, 0, 0, 0, 10, 10, 10, 20, 0, 0. So this is my soccer ball. Okay, so now let me show you the convolution of the soccer ball with the top left side of the, right? So like I said, convolution is you multiply the two inputs and then add them up. That's all there is to convolution. So what will happen? I'll do 10 times 10, as you can see, right? That was the first pixel over here with this pixel. Then multiply the second pixel, 20 with 5, then 30 with 0, then 40 with 20. Okay, I go to the next row, 10 with 0. Then I have 10 over here, 10 over here, 10 by 10, plus 10 by 20, plus 0 times 30. I go to the third row. This is 0, this is 0. 10 times 10, this is 0. I go to the last row. 10 times 1 plus 5 times 20, and then 0 and 0, right? So what will my number come out to be? This is 100 plus 100, 200. This was 0 plus 800, right? So 1,000 is the first row. Second row, this is 0, 100, 200, right? Then 100 here, then 110 over here. If I add everything up, what does it come out to? 1,410. Okay, roughly speaking, right? So anyway, so that will be the convolution at this point, 1410. Okay, so remember, just like my previous example, what do we do? Now we will slide the soccer ball 1 pixel to the right. So we'll keep sliding the soccer ball, keep doing the convolution, then we'll move 1 pixel down, we'll keep, so I will compute many of these, these numbers. So what will happen once the soccer ball appears over here? Exactly over here, okay? You'll see now there's highest overlap, okay? So this will produce the highest convolution. where the soccer ball is. So if we did like, suppose we do the convolution of two things, and if we take a look everywhere, there will be numbers 14, 10. Once I move the soccer ball 1 pixel to the right, the soccer ball is moved over here, for example. I'll do one more convolution. Suppose it produced 1285, right? And I keep doing it. Where exactly the soccer ball is, if I computed that value, I'm just giving you an example, maybe will come out to 29,185. And if you compare to all other values, most likely this will be the highest at that point. Okay, so you can see from image processing point of view, convolution is very easy to compute. Just multiply the corresponding pixels and add. Okay, so once again, don't be intimidated by this integral. Okay, again, all it means is multiply the two things, this part, and do the integration. With pixels, what happens to this? This becomes summation. And this is your pixels for the first image and pixels for the second image. You just correspondingly multiply and add, and that is what the convolution is. Okay. So coming back to our overall architecture of our CNN. So the idea is keep doing convolutions over here, convolutions over here, convolutions over here. The example that I gave you for the convolution right now is determining where there is a highest overlap or highest similarity, right? But depending upon what the two things we are doing the convolution with, for example, let me just sidetrack and give you one more example. Okay. Okay, let's take a look at stock market data. Okay, stock market data. For example, if we're taking a look at, let's say, price of IBM stock, and here on the x-axis are the days, y-axis is the price, right? You'll see, let's say today the price is 205, tomorrow it changes up. So it will be, every day was going up, down, right? So people who play the financial markets, they are interested in how is it trending? Because day to day, you cannot make a decision. One day it's up, other day it's down. They want to see, is it a good time to buy the stock? You want to buy it at a lower price and you want to sell it at a higher price to make a profit, right? So what we try to do is we try to denoise the data. Okay, one very, very simple technique is, meaning by denoising, what I mean is we want something like this, smooth, like curvature, so that you can see, it is trending up or it's trending down, for example, over here. As it starts to trend down, maybe you'll sell it at this point. Okay. The daily fluctuations we want to remove from the stock and, see how on a weekly basis or a monthly basis, how it's doing. Okay. So one possibility is you measure it, the value over here, then you go 1 week later and measure it over here. But again, that data will show you sometime up, down. That doesn't tell you the trend. Okay, so the denoising that we do typically is using, for example, a moving average filter. Okay, a moving average filter is very, very easy. Okay, suppose on day one, the price is 205, next day is 207, next day is 201, next day is 203, next day is 208, right? It's moving up and down. So what you will do is you will decide how many days you want to take the average. Okay, for example, you may decide 5-day average. So you'll go to the 5 days and add them up and divide them by 5. Okay, suppose the next day is 211. So after you compute the first value, which is the average of the first 5 days, how will you compute the next number? Shall I go to the next 5 days and compute the average? Or shall I go second to the 6th day and compute the average? Okay, and that's why we call it moving average. We don't go to the next 5 days because then it will again become discontinuous. Okay, so we go from 2nd day to the 6th day and compute the average of these numbers. And that gives you your second data point. Okay, meaning average of 207 plus 206 plus 203 plus 208 plus 211 divided by 5. And you get the idea. Suppose next day is 209. Now you will take the average of the 3rd data point to the 7th data point and so on. So if you do that, then what you will see is, and if you plotted this data, this moving average data, you'll see it is a lot smoother. And it gives you a much better idea of the trend of where it's going. Okay. So now let me take this simple concept, which is a known concept in the stock market, this moving average, to decide where the trend is, and show you it is actually a convolution. Okay. What if I say create one signal, 1, 1, 1, 1 is your signal divided by 5. Okay, meaning, remember here we have 5 data items, first 5 data items. And what is convolution? Multiply it together. For discrete data and add. For continuous data, you integrate. So what is it going to do? It's going to do 1 times 205, right? Plus 1 times 207, plus 1 times 206, because my first signal is all ones, 5 ones, okay? Plus 1 times 203, plus 1 times 208, and divide by 5. Or you can think of it this way. Each value, instead of being 1, is 0.2. Then you don't have to divide by 205, okay? So the first thing that we pick, in this case, 0.2, 0.2, 0.2, 0.2, 0.2, or 11111 divided by 5, we call this a convolution kernel. Okay, so as I mentioned to you, if you pick convolution kernel to be all ones and divided by the total number of ones, what effect does it have on the input? It removes the noise. It removes the daily noise. It smoothens it out, okay? So to summarize, what I'm trying to say is, depending upon the convolution kernel. And when we say kernel, basically one of the inputs in convolution. That's what we mean by, right? So depending upon what the convolution kernel is, right, it will enhance the data in a certain way. Okay, as I mentioned to you, suppose you're given stock market data. Again, going back to the IBM example, 205, 207, the daily price. Okay, you are given it for, let's say, 100 days. Okay, and your goal is to smoothen this data. remove the daily noise so that you can see which way it's trending. If you picked, let's say, a 7-day moving average kernel, what value will you pick in this kernel? 7 ones divided by is your kernel. So this is an example of one-dimensional data where the kernel is 7 ones, your data is all linear set of numbers, right? Same way we can have a 2D kernel, okay? For example, if I go to images, where, as I mentioned, images are a collection of pixels, right? Each pixel has a value 0 to 255. So there are a bunch of numbers over here, bunch of numbers, second row, third row, right? Each number will be between 0 to 255. That's how the pixel is. So image is basically 2D data. Okay, suppose the image is, somebody gave you a picture of this with, some other, let's say there's a car or a truck over here, right? Okay, and now we do a convolution of this image with some 2D kernel. So now the kernel will be two-dimensional. Okay, suppose that kernel is 1, 1, 1, 1, 1, all ones over here, divided by, let's say there are 3 and 2, 5. There are so this is a 5 by 5 kernel. So I'll divide by 25. Okay, and I apply 2D convolution to it, meaning I put the kernel over here, then I multiply, add the pixels and go to the right. So can you tell me what effect will this kernel have on this image after I do the convolution of this 1 by 1, 1, 1, 1 kernel to this image? What will it do? Okay, let me take you back to the stock market example. Okay, in the stock market example, if you plot the original data, like I was saying, the original data will be fluctuating every day. Okay, after I apply this type of kernel, what will be the effect? It will smoothen it out. It will remove the noise, right? The quick changes will become smooth. So whatever, so it will follow a, smooth transition, high to low or low to high. So same way over here, isn't this also going to remove noise from the image? Okay. If there's a sharp change over here, like daily change, what does the 111 type of convolution do? It removes that change and takes a look at how is it, right? So in images, the net effect would be, okay, suppose this image was given to you and you did a 1 by 1 kernel. What it will do is it will basically blur the images, because anytime there's a sharp change, like this is the picture of tree, right? Compared to the background from going from here to here, there's a very quick change. So the 111 type of convolution, which is like an averaging type of convolution, blurs, it will make this edge go change gradually rather than changing immediately. So you will see a blurry picture of a tree if you did this, right? So that is if we pick the kernel to be all ones, okay? Very similarly, if we pick the kernel to be something like this, what what you will see is it will change the image, a blurry image, to a very sharper images. Okay, so again, depending on the kernel, like I said, it will either blur it or sharpen it or enhance it some other way. So that is what the convolution does it, right? Now coming to our, let's go back to our convolutional neural networks. So today I'll just give you the motivation for it, and then we'll go into the math and the programming details later. Where did my picture go? Right here. Okay. Okay. So think of it this way. Perhaps the first convolution we apply, and now let's make this an image. Okay, perhaps the first convolution we apply, let's say, enhances the vertical images. Sorry, vertical edges. Let's pretend. The second convolution we apply, let's say, enhances horizontal images, meaning if it's a picture of a tree, okay, the first convolution basically made this part pretty clear, right? Now we go to the second layer. Suppose now it made the horizontal part clear, okay? Let's say we also wanted to recognize what kind of tree it is, not the fact it's tree. Is it an evergreen tree? Is it like a pine tree or whatever, right? Then we also want to know how are the leaves, within the green category. So maybe the next convolution further does, and if there are some smaller things, enhances those things over here. So that is the idea behind all these convolutions. Keep enhancing the image until it has clarified exactly what we wanted to recognize, and then pass it through a classifier, and we'll tell you exactly what kind of tree it is. Okay. So overall, that is the idea. Now, the question is, how do we know what convolution it should do in the first layer? What should it do in the second layer, right? As I've talked about before, what is the definition of AI? The definition of AI is we don't create formulas. We just give it the data and we say, here's what this data is about. You adjust yourself so that you recognize it better, right? So AI is, like I keep saying, it is learning from data. Okay, so what convolution should it do in the first layer, second layer, third layer? We don't tell it. We, in fact, will create a kernel and we will randomly initialize it. So obviously it will do a poor job in the beginning. Okay, then we'll go to the second layer. Same thing, randomly initialize the kernel. Okay, remember at the end, it will produce some actual output. We will still have a target. What are we trying to have it recognize? We will still have a loss in a classification problem. What will be the loss? Mean squared error or cross entropy? Will be cross entropy. Now, here's the interesting part. When we go backwards, remember, because all the convolutions in the beginning are random. So obviously this loss will be very high. Now we will go and say, okay, now start adjusting yourself. As we go back, what will it adjust? No, over here. The weight matrix, which we already talked about, right? W equal to W, whatever the old value was, minus lambda partial L over partial W. Okay, so this we already are experts at, correct? Okay, there's one more weight matrix over here. Okay, of course, we know how to do that as well. W1 equal to W1 minus partial L over partial W1, right? So now my question to you is, as we go back, what do we want to adjust? There are no weight matrices over here, the kernels, okay? So now we wanted to do kernel 1 equal to kernel 1 minus lambda partial L over partial kernel 1, kernel 2 equal to kernel 2 minus lambda partial L over partial kernel 2, right? So that's where it becomes challenging, okay? Because weight matrices were easy. We saw it in individual neurons, then we converted it to a matrix form. This was piece of cake, okay? This one, I'll quickly show you. So if we go to our .cpo 586. Hey, so if I go to right, I'll move this handout to the our 2024 lectures, but right now it is under 2019 lectures. So if I log in, okay, so somewhere over here I have CNN architecture and backpropagation for it. Okay, so anyway, I'll go over this in details of the next lecture. So there are some convolutions being done over here, convolutions, and so on, right? Okay, so as we go back, where did it go? Okay, so first, just like we have the forward pass, the usual go through one convolution, and you can see there's a summation, there's a multiplication. Why there are two summations over here? Because now we are dealing with two-dimensional data, right? So one of these is a kernel, as you can see, one is the input image, and we are doing the convolution. So this minus u minus v, as you can guess, can you guess what that's doing? It's doing the shift. Because remember, convolution is shift, multiply, accumulate, okay? So again, I can clarify this, so don't be intimidated by the math. Really, it's, and it gets a little more involved. And so as we go the backprop, the first part of backprop is very easy, okay? For example, what is this over here? For which one? The last layer, right? The softmax, right? And then, like I said, the W transpose times delta would become the delta for the previous layer. So you guys already, so now you're beginning to see, hey, the math is not that bad. Okay, so anyway, but like I said, as we go through and now we have to figure out how do we compute the derivative. This delta means the derivative in the kernel. Now the math becomes a little bit intimidating, okay? So you'll see now it became a lot of different things and rotations and so on. Okay, so to summarize, see, anytime I see something I want to learn, right? I always try to implement it myself because otherwise I feel I didn't understand it, okay? So same thing, if I go back 2012 or 13 time frame, CNNs were becoming very popular, okay? Everybody is talking about it. So I started looking at it. And if you read an article, there are a lot of articles on the web. And of course, it makes easy. I come from electrical engineering background, so convolutions are natural to me. So I'm able to see the idea. I said, yeah, it's not too bad. I will just do convolutions, have it learned. Okay, but then I sat down to program it. Okay, and it will never work. Okay, and I'm looking at the code, going back to my math. So all these is a hand equation that you see I'm trying to program, right? And and I'm pretty decent software developer. I'm take great pride in it. No matter how the complex the software is, I'll be one of the quickest one to develop. And here I'm stuck at this for months. Okay. So finally I keep resolving my error and, see there's some rotation going on over here, which I was not, in my math, I had an error. Okay. And of course, you take a look at the internet, nobody has these equations. Okay. They all just show you, people who developed it, I'm sure they knew it, but they never published it. They never clarified it. Yeah, I'll show you the original CNN paper by Jan LeCun. He's one of the pioneers, probably next person to get a Nobel Prize. His paper will show you, oh, we did this on MNIST dataset, 2005 famous paper, no equations, right? So anyway, after struggling for 2 months, I finally figured out my error. And then I was so happy it worked. 2 months of night and day programming and debugging. And then I said to myself, okay, I already have this theory in front of me that somebody else created. And it took me 2 months to really understand and program it. How difficult it would have been for the person who created and actually showed that CNNs work. So I said to myself, that person should get a Nobel Prize, honestly. So I came to one of the classes and I also, shared with the students. And the next day, they announced the Turing Award, which is the equivalent of Nobel Prize. And Jan LeCun was one of the ones who got this. So I felt, in a way, good that the struggle I went through, it wasn't because I'm not good at it. It really is a complex thing. But anyway, ideally, I would like you to go through and program it yourself. But then, we have so many other things to learn. So at least I'll explain in the next lecture how it works. But with our today's background, where we got a high level idea, now we can put slight more detail to it. And hopefully it will make more sense. Then we can start to use the libraries because otherwise it will be months before your code will be ready. Okay. All right, so I'll stop here for today. Oh, just a quick announcement. As some students mentioned, next week is a big holiday for you guys. So we won't have a class next week, and we'll have a midterm exam, a short, easy exam the following week. Okay, so no class next Saturday, following Saturday. So please review everything. No CNNs on it, but anything before CNNs for standard neural networks, batch normalization, dropout, overfitting, backprop, matrix form. So please review all of those.